Good morning. Am I live? Am I on? I don't know. I think so. It feels like I should be. Therefore, I acknowledge the traditional owners of this land, the Whadjuk Noongar peoples. I pay my respects to their elders, past and present, and to Aboriginal elders and peoples from other communities who may be taking part in this live stream today. I'm hearing lots of squirrel. Okay. I'm getting notifications. Where are the notifications? Oh, they are coming up in Discord. Cool. Okay, that is something that we will get to because that is Henrik with with some information about the stuff that we're going to be doing today. Good morning to Michael, Outside the Box, Mitchell, Michael again, Stephen, Delane, Amanda. I hope you're feeling a whole lot better, Amanda, and that your recovery is going well. Imi's here, Keith, Mitchell, Justin C, Russell. Okay, so, and Gerald is here. Hello, just back from America. And Paul, David, good morning. Okay, just need the right size OLED. Okay, I'm just reading a message from Henrik. Now, do I jump straight into this? Feels like I always take ages to get into whatever the topic is that I'm doing on a stream, so it feels like I should do something for like the first 20 minutes or half an hour that is off topic and then eventually get to it. Gavin, you're here as well. Excellent. So what I've got is, what I have for you today is a continuation of this. This is the one of the many things that Henrik posted me from Estonia. It's a kit for a little DIY oscilloscope that he designed a while ago, a couple of years ago, it sounds like, 2.5 years ago. Yeah, so there is, and I have, let's see, what can we do here? And we have a function generator, and this is the little oscilloscope kit thingy. Got a couple of Arduino compatible boards here and a genuine Arduino. Look, here's an Arduino NG. I pulled this out when I just grabbed my Arduino box this morning. This one is serial number 12,110. So it's getting up there in numbers. And yeah, I've got some much older boards than this, but this was just in my random Arduino box. Arduino NG for next generation. Because it had USB on it. I think this was the first Arduino with USB. They didn't even have USB until this model. So, or did they? I can't remember. And also I've got this, which is my Arduino oscilloscope thing from Practical Arduino. So maybe we'll check that out as well. Not nearly as nice as the work that Henrik has done. But it's kind of related, so we can see what's going on. And as Stephen says, a lovely bunch of coconuts. Right. We are all a lovely bunch of coconuts. I feel like a coconut. Scott says, do they have Arduinos in Star Trek? I don't know. They pop up in all sorts of places as film props. Yeah, when I was contracting to Beyond Productions, I'm just going to hit mute on this because I'm getting all these notifications from Henrik, and you can probably hear it. So the original video, right? Okay, he's posting all sorts of interesting stuff in the background, preparing for the oscilloscope trial that we're about to do. We will get to that. My glasses are terrible. Talking about stuff being dirty, this morning I grabbed the oscilloscope and I got flux all over my hands. I don't know if you remember, but last week when I was assembling it, was it last week? I think it might have been. I couldn't get the solder to stick very well to the surface. Oh, they're still terrible. The surface of the connectors. These connectors here. VNC connectors or whatever they are. So I ended up putting a bunch of flux on the bottom of the board and then forgot about it. What I really should have done is given these a run through the ultrasonic cleaner and then dehumidifier. before today, but I forgot. I picked up the board and I got flux all over my hands. So about 4 minutes before the live stream, I ran down the back and sort of just waved this around inside the ultrasonic cleaner. It was cold and the ultrasonic wasn't running. It was just, yeah, it was just the fluid from it that I was using to try to wash off some of the flux. And I only dunked it in there for about 30 seconds, so I didn't do a very good job. And then I was hitting it with the hot air about 30 seconds before the stream started. So I'm probably going to put on gloves or something before I continue with doing that. As Mitchell has said, that would have required pre-thought or planning. Yeah. I failed on that respect. Henrik, yes. Henrik is in the chat. So, what are we doing? Okay, what are we doing? Now, first thing is I need to put some more parts on this because I've got to put the pin headers on to plug it into the Arduino. As you can see right here, I didn't put headers on it last week. I just put on the parts for the oscilloscope, and it's got some buttons there. I have no idea what the buttons do yet. We will find out in due time. This is going to be a voyage of discovery. So I need to put the headers on it. What else do I need to do? Oh, yeah, the OLED. Okay, I just need to grab an OLED. Now, oh, thanks, Mitchell. It's encouraging. Mitchell said, "You did not fail since you did something 30 seconds before the stream started, so success, partially." Right. Now, this... let's have a quick look at the code. It looks like what I need is a 128 by 64 OLED with an SSD 1306 driver chip. I can tell that because this is the code that Henrik just sent me. And let's have a look at, is there a, can I just zoom in without, let's see. What I want to do is zoom, increase font size. Oh, I can. Okay, so Command plus. Yes, okay. I didn't want to have to go into preferences and change the general settings in there. So I'll leave the general settings unchanged and I'll just zoom in here on the code. Alright. Hopefully that'll make it a little easier to see on screen, because this stuff doesn't come through very well on video. Alright. So Henrik said that he got it from radiopench.blog. This one here. Let's see what this opens. Okay, looks like a Japanese site. Bring this one up. Needle Nose Pliers, a diary of an uncle who likes to tinker with things. So let's see, ESC, blah blah blah. Okay, my guess is that the link, oh hang on, what am I doing? It wasn't a link to a specific page, it was just a link to the blog. And this is April 27, 2020, so it's been a while. Alright, uses the Adafruit SSD 1306 driver. That is for an I2C display, and we can tell from these settings here that we need a display that is 128 by 64, which I think typically means one of the little 1.3 inch displays. Rec length 200, size of wave data buffer, cool. Minimum trigger swing 5, display unsync if swing smaller than this scale, okay. Declaration for the display, set up the display, and range name table, range V name, range H name, so it's got different ranges. That's pretty cool. It's been some thought put into this. Certainly more thought than I put into the project that I did. So we've got a wave buffer, display string buffer, scales. Henrik says to look in Discord. Yes, I can see there's a video there. I am keeping an eye on what you're putting in Discord, Henrik, so I do see it, and I'll bring it up in a minute. There's a link to a video. So there is a voltage range. What have we got? Hold. Now, one thing I don't know is what those buttons do, but hopefully the code will start to make this clear. Button pressed interrupt, pushed, no, button pushed interrupt. Select button, up, down, hold. 1 of 10 attenuator, LED. Okay, so we initialize the display, load EEPROM, last settings. Oh, it even uses non-volatile storage to keep settings, starts the screen. Set conditions, digital write, read wave, set conditions, analyze, write common image, plot data. Oh, excuse me. Time for some more caffeine. Speaking of which, here is the first squirrel for the day. I'm tired. This is just like a personal aside. For some reason, I have ended up not being able to sleep very well over the last little while. I think it's partly a combination of discomfort, like where I'm staying at the moment. I don't fit in the bed. It's too small. I physically do not fit, and also just my brain won't turn off. So what happens is I get to like 11 o'clock at night and I'm feeling tired and I know I should sleep, but there's stuff that I just want to do, like look, working on feeders or for the pick and place machine. I have a feeder session right now. I'll probably get into that a little bit later. There is a whole lot of stuff going on in feeder land at the moment. I know I've mentioned this in the past on previous streams as well. But so I find myself at like 1 o'clock in the morning looking at CAD files for other people's feeders designs and drawing sketches and figuring out what I can do to make one that does exactly what I want. And I'm there thinking, I've got to wake up in a few hours and I have to be ready to do a live stream, and I just can't turn my brain off. I need to do something about it. It's kind of a mental spiral spinning condition. Alright, talking about set conditions, measuring condition settings. So we're string copying. Okay, we've got some ranges, setting of range. We've got a little state machine. Okay, so set conditions is a state machine, or it's a function that changes the states in the state machine. So we've got a switch based on VRange, and we can set different options based on the VRange that's been selected. So 50 volt range, 20 volt range, 10 volt range, etc. Scroll down, 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 down. Write common image, common screen image, erase all. Yeah, that's a whole lot of stuff we won't get into. That's what will make it look funky on the screen. Read wave. Okay. This is probably one of the more interesting parts of the code. Also, Mitchell says, the lack of sleep is a problem. I feel you. I'm watching this stream at 2 a.m. while looking at 434 megahertz stuff for a remote squirrel project. Lol. Sometimes I wish someone would knock me out. Yeah, that's how I feel too. Yeah. Oh, Imi said, this is in response to that. Imi says, big mood. Try listening to a podcast or something that will engage your mind when you're going to bed. It helps the mood to focus on not your own thoughts. Yes, and I do that. I listen to podcasts a lot. I go through so many. I'm currently on my third listen through of The History of Rome, the classic. It's such a good podcast. I love it. It's how, okay. I wonder if I can find it online. I'm sure I can. Where is the History of Rome podcast? Mike Duncan's The History of Rome podcast. Let's see. Oh, it's still on TypePad. Amazing. So TypePad was where it originally went up before he had his own domain or anything. Tours. Yes, I know we are way off topic here. Update 1 year later, an AMA from 2013. Where are audible recs? Audible book recommendations. No, what I was just looking for was a list of episodes. Okay, so one episode, and you can see here the first episode was first view like 11 minutes, 16 minutes, 18 minutes, 14, 15 minutes. Okay, so that was how it started out. The episodes were all about that long. And then, oh no, let's see, all 10 more episodes. It'll take me forever if I keep clicking on show 10 more episodes because there are hundreds of episodes. So you can see here they're starting to get a bit longer. First Punic War in 2 parts, 22 minutes, and then Interbellum 15 minutes, 10 more episodes. What I find really fascinating about this particular podcast, in fact, yeah, that's going to take too long to do that. I'm actually going to pull it up on my own. Yes, we're chasing squirrels. This one, where is it? History of Rome. Got to find it on my enormous list of podcasts and get through the ads. All right. How many episodes were there? 179. It was actually more than that because of the way it was numbered. There were a few that were like part A and part B. It's something like 200 episodes, and some of them were quite long. It was, I don't know, it's probably like 100 hours, give or take. That's just my guess. There's probably 100 hours of content on it. But what I love about it is that it traces the line through from the early days of the establishment of Rome as a city through to, where does it end? Somewhere in the Middle Ages. And it really shows the context of so many things that are in our world today. So, yeah. And because this is my 3rd time through listening to it, I don't mind if I miss little bits. So sometimes when I'm trying to go to sleep, I will put on, or late, I will put on History of Rome, and I'll be hearing about something that was going on. So at the moment, I'm up to the rise of Constantine, which I think was around the year 342 CE. And how Christianity took over the world, basically, which is fascinating. Yes. Okay, where are we? We cannot restart our brains. Yeah, Zumi says, yeah, something that you don't mind missing bits of is good. And Chip says, I use Podcast Addict app, which has a built-in sleep timer so you don't miss too much. That's a good idea. All right, where are we? Let's have a look at this oscilloscope thing. Right. Back to the link that Henrik sent. So this is a YouTube link. Arduino oscilloscope built on a breadboard. Is this the original one? I've got the sound turned off at the moment. I'm going to unmute it. I've got no idea what. Okay, it's just music. All right, so we're not missing anything. Final parts installation start. So my guess is that I think this is what Henrik based his design on. So it looks like the original was done. Oh, you copied the link wrongly? Okay. Yeah, so this is the original design, which was done on a breadboard, and then Henrik has designed a PCB, which is the equivalent circuit. I think that is the way this goes. And it looks like he's got 4 buttons on there, so there's a button up on the top left, there are 3 across here, different function buttons, and he's got different colored buttons. I really should get myself like a range of different colors. That looks like an input, a probe, assembly completed. Okay. And I wonder if I'm going to get YouTube copyrighted for showing it. Oh, look at that. We got a scope. Oh, look at all the information it's showing. It's got frequency and duty cycle, and that's really cool. It's put a bit of work into that display. That's nice. I better stop doing this or I am going to get copyright striked for stealing content. Yeah, so there is also this link, which is the one to the specific post. So the link that I, where are we? Yeah, so the link that we were looking at before was just this one, which is the link directly to his blog, but there is also this. I made a pen type oscilloscope using Arduino before, and during the development process I checked the function with a breadboard. Yeah, frequency measurement function. Yeah, okay, so he's been adding features based on requests. There is the schematic for it. Let's zoom it in. So we've got hold. Why are there diodes? Okay, that is just a way of being able to detect different button presses. But yeah, that's kind of a strange arrangement. Odd, quite odd, considering that it's using 4 digital inputs here anyway. Why aren't they all just wired separately? I don't get it. Anyway, doesn't matter. It'll work like this. So we've got the OLED, and he's used an Arduino Nano. There's a Schottky diode on the input, and on the external 5 volts, so that's just power in. Oops, sorry. Then we've got signal in coming through a 510K, there's a 12K and a 120K. So we've got a voltage divide, so it's a voltage divider between the 510 and the voltage divider is sort of turned sideways just to make it look confusing. Imagine this was all rotated 90 degrees to the right. So we've got a voltage divider with the 510K on the upper side of the divider, the 120K on the lower side of the divider, and then there's a bias coming in here. So that would allow the voltage divider to be pulled in a certain direction. So that is going to be like an offset. It would, it kind of makes sense like this. Okay, let's look at the signal path. I'm going to, now that I've kind of mentally cogitated what's going on here, let's zoom this in. Not do that. Move this up. All right, so starting again, signal comes in here on the left. It passes through a 510K resistor, gets to this point where there's a junction. Now for now, totally ignore this top part. Just imagine that it doesn't even exist, R3 with this 12K resistor. Okay, so then we have a junction with a 120K resistor that pulls down to ground, and then the signal continues on into A0, into this analog input. So what this provides us is a voltage divider on the input, which is going to reduce the voltage from the signal to what is presented on the analog input. And that will allow it to read voltages that are above the range that the analog input could normally read. Yeah, Johnny says that schematic does not make much sense. Yeah. Yeah, it's the layout is kind of strange. Okay, so now we have a voltage divided signal coming into the analog input, and then by reading that input repeatedly, we can see, well, reading it once, we can see what the voltage is, and because we know the values of the voltage divider, you can do the calculation to figure out what the original voltage would have been. So at that point, by reading A0, you can see what the voltage is of the signal that you're being supplied. And then, by taking multiple readings over time, so basically an oscilloscope is just a multimeter with a memory, with a sense of time. it takes a voltage reading and then waits a certain period, takes another voltage reading, waits a certain period, takes another voltage reading, and then you can see the trend of the voltage over time, and that's what the oscilloscope is showing. And so by taking multiple readings, we can generate a waveform by taking the signal that comes into A0. Okay, so what D12 is for, and there is a 12K resistor here. I may be wrong about this because I haven't, my total knowledge of this circuit and what it does is exactly what you have just seen. It is looking at this schematic and quickly looking at that source code, which we haven't even finished looking at yet. I think what this is doing is using D12 to apply a bias voltage to this voltage divider so that it changes the range. So it's like a low range and a high range. So if it's if D12 is open circuit, so high impedance, say you set it to be an input or something, it doesn't matter what, basically just you're not driving D12, you're leaving it open circuit. What that means is that this resistor is not going to have any effect whatsoever. And then here it says high Z, which is high impedance. It means that it's 1x or 1 times at high impedance. Then what happens is if you drive D12 low, so that's pulling it to ground, so 0 volts on the side of here, effectively what happens is that this 12K resistor and this 120K resistor are in parallel. So they form a voltage divider to ground, and it dramatically changes the bias of the voltage divider. So the ratio, instead of being 510 to 120, becomes 510 to 11.8 or something. It's just under 12. So what this is doing effectively is giving a switchable voltage divider so that you can have a range of 1x or you can have a range of 1/10. So it reduces the signal to 1/10 of the reading that it would have been reading before. Henrik said D12 is not PWM. No, it's not. It's just being used as a ground bias on this voltage divider. Yeah. Right. So, yeah. Part of the reason that this is hard to understand is that this schematic is drawn in a way that is really not that clear. In fact, I think I am going to, just looking for a piece of paper to draw a diagram on. All right. And some colored pens. It's time for some sketching. Where is I had a notepad here somewhere. Oh yes, here we go. Here's a notepad. And I'll switch to, where? Switch to that. All right. I will do my attempt at restructuring this. So we've got, what'll I use? Blue? No, I'll use green and red. So, I don't like it. That's just the color code. All right, I'm going to use blue. That's it. Decided. And just for simplicity's sake, I'm going to draw resistors as boxes, so I can stick the values inside them. All right. So then we've got another resistor. So this one is 120K. And then this comes along, and then we've got the Arduino over here. That is A0. And this is the analog input. So it's reading a value between 0 and 5-ish volts, depending on the... anyway, let's not get into that. There are different ranges you can set depending on the VREF on the analog input. That's not important to what we're talking about right now. Okay, so this forms a voltage divider. In fact, I don't like that. I said I was going to try to draw it better than the original, and then I failed. So it should be like this. This one is 510K. Comes down to a joint, comes across to here, then the Arduino, and that's A0. Then there is a resistor here, which goes to ground. That is 120K. Okay, this makes the voltage divider much clearer. It's much easier to see what's going on. Ignore the rest of the circuit. So if we're looking at this part of the circuit around here, we've got R1, 510K, R2, 120K. That is the voltage divider going into analog input A0. So that is what we have here. 510K, 120K. Voltage divider going into A0. It's just that I've twisted that around to make it more clear that this is a voltage divider with the high voltage here, 0 volts here, and what we're tapping off is the midpoint. Then this is the trick with the other resistor, and I'm going to draw it a bit differently. So this is the 12K resistor. Okay, now at the moment this side of it doesn't go anywhere. So if this is just left floating, I'm going to draw I'll use a green line for this. And this comes across to, what pin is it? D12. Not that it matters, but okay, it's going to digital pin 12. Now, if digital pin 12 is in a high impedance state, this resistor, this side of this resistor is floating, and nothing happens. It's like it's not even there. So the signal that you get coming out of here is the function of this voltage divider. Now, if this is driven to ground, then effectively, say you take D12 and you set it to, you drive it low, effectively it's the same thing as if you had connected this resistor, the bottom end of this resistor, to ground. And now what you have is a voltage divider with 510K on the top and 120K and 12K in parallel on the bottom, which will be just a little bit under 12K. Without doing the calculation, it'll be like 11.8K or something, 11.5K. So the ratio of the voltage divider is then totally different. It's basically changed it by 10 to 1. So it'll be 1/10 of the signal strength coming in when this is set to ground. So that gives you a higher voltage range on here. So say, I'm just going to make up some numbers. What is it? 5, so voltage, say, okay, let's say we had a range of 0 to 10 volts normally, and then you switch it so that this is grounded. The voltage divider then becomes much stronger. Now you've got a range of 0 to 100 volts. So that D12 is being a range selector. I don't know if that made any sense. Did my description make any sense? Johnny says set D12 to high and it falls apart. Yes, it most certainly does. Is that a Sharpie, Mr. Squirrel? Yes. Okay, yeah, I hadn't even thought about red-green color blindness. Yeah, so on this, so this looks like it was done, yeah, sometimes you can tell what software was used. Just looking at this, to me, this looks like it might have been done in Eagle, and these look like the default colors for schematics in Eagle. And these traces are in green, and then the parts are in red. So for people who are red-green colorblind, yeah, that would not be a good combination of colors. Okay, nice. Paul and Gerald said that my explanation made sense. I may not even be correct, but hey, I can be convincing at least. Yeah, okay. Oh, Celtic Bee says eagles only see in black and white. Yeah, probably very, very high resolution. A lot of machine vision stuff is done in black and white. Oh, Henrik says also Easy EDA uses the same color codes, etc. Yeah. Okay, so then, okay. I'm going to, just in case people are interested, I'm going to chuck this link in the chat because it hasn't actually been put in the chat. There you go. Right. And that's where this schematic came from. Now, where are we? Okay, back to the code. Back to the code. So this is what I'm curious to see. So maybe this will help illuminate a little bit about what's going on with that D12 and the pull-up. So this thing here with the comment says if 1/10 attenuator required. So if at 10x equals 1, then pin mode D12 is an output and you drive it low. Oh look, my guess was correct. Else it's just an input, yes. So if you don't need the 10:1 attenuator, then put pin 12 into a high impedance state. And if you do need the attenuator, set it to be an output and drive it low. So pull it to 0 volts. Nice. Switched H range. Delay microseconds. Yeah, some magic numbers in here. This will be to set the... so we've got 100 milliseconds range. And then, yeah, timing adjustment and timing adjustment tuned. Okay, so this is interesting. This is a tricky thing. When you're dealing with this sort of program, it's... dealing with time is a problem. And the execution time of the code, because the code needs to take the reading from the input and do its calculations and things. Now, if you make a, I'm just pondering different ways to explain this. If you ran blink, like say we went to Arduino examples, come on, open the menu, you can do it, it's an SSD, you can read it, basics, blink, and where's it gone? There we go. Okay, so it turns an LED on for 1 second, then off for 1 second repeatedly. And we can see here that what it's doing is waiting for a second in between each transition. Now, at face value, you would think that if you started this and left it running for a while, it would take, say you left it doing 1,000,000 blinks. So 1,000,000 times on for a second and 1,000,000 times off for a second. Each one of those cycles takes 2 seconds, doesn't it? And therefore, after 1,000,000 blinks, exactly 2,000,000 seconds will have passed. But that's not the case, because what this is doing is introducing a delay in between its execution of the code. But executing the code takes a finite amount of time. Just a simple digital write. It's very, very fast, but it will still take time. So the actual cycle here is going to be 1,000 milliseconds plus whatever time it takes to execute this code, which is probably like nanoseconds or something. But anyway, over time, it's very, very slowly going to creep. And so what happens in a more complicated program like this is if you want this to execute every 100 milliseconds, you can't do your thing and then delay for 100 milliseconds, because the code that is executed will have consumed some of that time. And so the interval will keep shifting sideways. So what we can see here is that the author of this code has put in a delay microseconds of 3,860 and it says timing adjustment tuned. and prior to that it was 3,888. So my guess is that what he did is ran the code and checked how much execution time was being spent in the code outside of the delay, so that once it goes into the delay, it's just padding the time. Now the other way to do this, if we go to example, so if you had, where are we? Digital Basics. Where's Blink? Where's Blink? Oh, there we go, Blink without delay. I haven't even looked at this sketch. I don't think I've ever looked at it. Maybe. Okay. Previous millis. Okay, so what this is doing is setting a time at which the transition should occur. So instead of delaying for 1,000 milliseconds, it checks how many millis have passed, how many milliseconds have passed since the last time it did a transition. So this should be much more consistent. Even if you did something in here, like say in here we added delay 100, like added 100 millisecond delay, that shouldn't cause any skew in this. With the other version of the sketch, we would see skew by adding extra execution time into one part of it, but the just saw, that calendar is still annoying. Even not confusing, correct. Okay. Just glancing at the chat, trying to catch up. Stephen said that's how the dinosaurs went extinct. They got the timing wrong in their program. Yeah. David said time creeps on all of us. Michael says, I see the concept of leap seconds being introduced as a squirrel here. Squirrel seconds. Yes. So what we're, with this, as long as this delay is below the period, like the interval, we've got an interval here of 1,000 milliseconds. So I could make this, 567 millisecond delay. I could add some random delay in here, and it wouldn't change the rate at which this flash occurs, because it is always going to occur at a certain number of milliseconds past the last time that the event occurred. So this is a very simple way of doing an interval-based scheduling thing. And as simple as this seems, this is actually the basis of a whole lot of real-time operating systems, like really basic real-time operating systems use this sort of thing, although in a much more complex way, because they set interrupts and things to, and they have ticks and like tick time and all that sort of stuff. Anyway, let's not get into that. That is getting off the subject. The whole point is this has been tuned to have a certain number of microseconds delay, so that we are working in a 100 millisecond time scale. And then down here you can see there's a 50 millisecond time scale, and it has got a smaller number of milliseconds in there. And here for the 20 millisecond time scale. Alright, so what are we doing? Time exec, approximate execution time. Okay, interesting. So that is part of the tuning process, it looks like. So then we've got ADC SRA. So this is ADC, obviously is part of the analog to digital converter. Set register, what is it? S register A? I can't remember what S stands for. Anyway, what it's doing is an AND operation against hex F8, and here doing an OR against hex 07. So it's basically doing some bit operations here, and this would be done so that it's fast, because when you're doing a program like this, you want this to execute as fast as possible. And so what it's doing is clearing the bottom 3 bits, setting the dividing ratio of 128. Okay, so this is setting some things within these registers for the analog to digital converter. It seems so many years since. Oh, Scott says, except that delay is a blocking function. It is, but it doesn't matter. Okay, maybe I haven't understood what your comment was referring to, but it's a blocking function, but that doesn't matter in my previous example as long as it is less than the interval at which you want the thing to repeat at, because the next time around it'll check how many milliseconds have elapsed since the last execution point for that part of the code, and it doesn't matter how long it has taken to get there, it'll still execute. The words I'm saying are kind of, they're probably in the dictionary, but they still don't make sense. Alright, now where are we? Up to rec buffer size for int I. So we're sampling in a loop and read and save approximately 112 microseconds. Yeah, so he's put a fair bit of work into figuring out how long these things take. So wavebuff I, what he's doing is reading however many samples. What have we got? Reclang. So whatever reclang is set to, I'm not sure where that's defined. So recording length, it is filling up a buffer with a series of analog reads on input 0. It's then doing this tune delay, and it's then checking for whether the switch has been pushed. Abandon record. This improves response. Okay. So then it just jumps out of the sample. And basically the same thing is done, same for each of these ranges. The difference here is, what have we got? We're sampling the same. The only difference in these ranges, so here we've got 10 millisecond range, 20 millisecond range, 50 millisecond range. This code, yoink, so case 2, that code is the same, just at first glance. I wonder if, yeah, it's the same as the code in case 3, with the exception of two things. One is the delay, and that is how it's achieving the intervals, and the time exec calculation here, which is just part of the tuning. So that's not actually functionally part of the code, or not part of the operation of this part of the code. Is just like introspection sort of stuff. All right, 2 millisecond, 1 millisecond, 500 microsecond. Interesting. So we've got delay microseconds 4 here on the 500 microsecond range, and we've got where are we? Time fine adjustment. Look at this. This is interesting. So this is where things get really curly. So at 1 millisecond, we've got a 10 microsecond delay. Once we get down into this range, a microsecond is not enough enough resolution. So we've got a 500 microsecond range. It's delaying for 4 microseconds, and then it's got time fine adjustment. This is clever. I like it's interesting reading people's code like this and seeing what they've done. So we've got a NOP. So NOP stands for no operation, and that is a so ASM is assembler. So what this is doing, what that command actually does, is nothing. But nothing takes time. When you have at the lowest level, as the processor is executing operations, it does a certain amount. I haven't actually looked up what this is on the AT Mega, but when you are running at a certain clock speed, say 16 megahertz, then you are getting 16 million pulses per second from the system clock, and depending on the architecture of the processor, it executes a certain number of of opcodes at that rate. I'm doing a whole lot of hand waving now. Because the thing is that I haven't actually looked at how this works at the assembly level on an AT Mega. I've done this stuff on a Z80 and on other processors, but never on an AT Mega. I've never gone below C on an AT Mega. So there is an operation at the lowest level. Every processor that I'm aware of implements this, which is called a no-op. And basically you are telling the CPU to do nothing for that clock cycle, or for that period of code execution. So the processor is stepping through a series of opcodes at a very specific defined interval. That rate is defined by the crystal, or by the oscillator. So here we've got a 16 megahertz oscillator, and it is going to be stepping through commands at a very specific rate, and it can't stop. It has to keep doing stuff. It has to execute exactly the correct... How am I saying this? I don't know. I haven't thought through how I'm explaining this. So what happens is that you can't pause a CPU. Now that's a blanket statement. There are exceptions. Let's not get into those exceptions. But just as a very general statement, you can't pause a CPU. It has to keep executing. So if you don't want it to do anything, you give it something to do called a no-op, and it does nothing. And then it moves on to doing the next thing. So if you feed it a series of no-ops, that will make it do nothing for a very accurately defined period of time. And you can see in the comment here, the calculation says that a no-op takes 0.0625 microseconds to execute with a clock speed of 16 megahertz on an AT Mega 328 processor. So by calling this series of no-ops, however many that is, 1, 2, 3, 4, 5, 6, 7, 8. So that is, oh, it's even written here. So that's 8 no-ops times 0.0625 microseconds, means that that is a 0.5 microsecond delay. It is just spinning, the processor is spinning its wheels, doing nothing, and you get to the end of that period and then it continues on. So that's a way of tuning the delay at a finer than microsecond region. So this is, yeah, you can tune it down to 0.0625 microsecond increments. Down here in the 200 microsecond range, I have very, very painfully failed to explain it previously, so I'm not going to do it again here. This is just the same thing. We've got no delay microseconds here, because the delay that we want, well, what it could have done is a delay of 1 microsecond and then put in 4 no-ops. But instead, it's just 20 no-ops to give it a 1.25 microsecond delay. And there we have it. That is what 1.25 microseconds looks like. Okay. Scott said, this code is a fine example of why real scopes use custom silicon. Yes, that's right. Gavin said, about now a spreadsheet pops up. Right. Scott said blocking is bad. Okay, yes. Scott is correct. Blocking is bad. To be avoided if you can. David T said, oh, this is in relation to a no-op. Just fetch, execute, do nothing. Yeah. And David Crisp said, halt and catch fire. Right. That's a classic old one. Stephen W says, you can pause earlier CPUs by just not connecting the clock. That is correct. That is one of the squirrels that I said I did not want to chase down, because there are exceptions. You can do that on the... Okay, it comes down to a couple of factors. One is the the process that was used, like the base technology that was used in the processor, and the other is the base technology that was used in the memory. Because with dynamic memory, you have to read it in order to keep it alive. So if you simply pause a CPU with dynamic memory, typically its RAM will end up being wiped. But if you have static memory, then you can set values in static RAM and just keep power applied, and it will hold that memory indefinitely, whether you're running a clock or not. So with a lot of early processors, things like Z80 based systems, you could run them down at super slow speed. You could run a little, like a really basic square wave oscillator as a clock and make it variable, and you could change the speed of the computer and run it at like kilohertz if you wanted to. Scott says, never try to pause a multi-threading CPU. Won't end well, yeah. Yes. Oh, Paul Gray said 1/16 megahertz equals 0.0625 microseconds. Checks out on my calculator. Cool. I was just taking it at face value and faith. I didn't verify, but you're correct. All right, so oh, Gavin said, so if you were to change CPU to an ESPXX, all of your calibration would go to crap? Yes, exactly. This is very specific to the target processor. So this ASM command, or assembler, it's running a single no-op execution. So that would work on I guess that would work on an ESP, because I guess they implement the no-op. It's just my assumption. But this calculation would be totally wrong, because it's running at a different clock speed, and we don't know how long it takes for a no-op to execute. Well, we could find out. We could work it out. It's just not it's not this. So you need to know the clock speed of your processor and how long a no-op takes to execute in terms of clock cycles. Dodgy! Good morning, Dodgy! Oh, Scott says, I may be losing my will to live messing about with RP2040 stuff. Really? Has that been a painful experience? I think I mentioned this a couple of weeks ago. I designed an RP2040 board, my very first one, a few weeks ago, and I was shocked when V1.0 of the board worked straight up, no problem. I assembled it, plugged it in, it appeared on my computer as a mass storage device, and it all worked. I stuck MicroPython on it, I ran Arduino code on it. Yes, Henrik, we'll get back to it. Yeah, and I was surprised at how smoothly it went with the RP2040. I liked it, but I've only done very, very basic stuff, so yes. Oh, Michael pointed out, even minor voltage variation could throw this out. Yeah, voltage variation. Are you talking about the timing or the calibration on the voltage scale? I don't know. Okay. Ooh, voltage variation. It should be consistent in terms of timing. With an 18 mega, you can run it at 16 megahertz down to, what's the voltage? It's around 4 volts, I think. It's a long time since I've looked at that data sheet. So one of the reasons that if you look at the early Arduinos, some of them ran at 8 megahertz. And that was because they were running the CPU at 3.3 volts. Like if you got an Arduino Pro, what was the model name? I can't remember. Yeah, I think it was just Arduino Pro, 3.3 volt. It ran at 8 megahertz. So, and if you did use this, then of course your timing calculations would all be out, and the interval would be double that, because because the period is twice as long. All right, data analyze. Yeah, Stephen W says, hit or miss if it will run 16 megahertz at 3.3. Yeah, it's definitely out of spec. I remember that much. So an 18 mega is spec'd to run at 20 megahertz from at 5 volts. And then as you decrease the voltage, you have to decrease the frequency as well. But 3.3 volts, it is definitely out of spec for 16 megahertz. Oh, unexpected sneeze. I got to the mute button just in time, I hope. Yeah, anyway, data analyze, get various information from the waveform. Ooh, this will be interesting. All right, so data min 1023, data max 0. Min value initialized to a big number, max value initialized to a small number. That's funny. It feels backwards, but that totally makes sense. So what this is doing is, my guess is that these numbers, that number is going to be pushed down and this number is going to be pushed up as we proceed through the code. So what this is doing is resetting the minimum value, the data min, and the data max. So max is 0, min is 1023. So what would happen is, yeah, here we go. It's in the next part of code. If I just read on, the answer would be self-evident. So what it's doing is cycling through the buffer, so wave buffer, and however many there are, rec length, recording length, and if that data is less than the data minimum, then that becomes the new data minimum. So data minimum starts out at 1023. If it's less than that, then that becomes the new minimum. And then what this does is provide a very elegant little, a very elegant way of looping through a series of values and finding the minimum value. And this is looping through values and finding the maximum value. There are other functions that can do this. Like there are, I think in Arduino there is a function where you can pass it an array and get the min val out of the array. But this is probably just faster, maybe. I don't know. But it's a yeah, it's an interesting little thing to see, that technique. So by the end of this, once you get to the end of this loop, data min will be set to the smallest value that has been seen, and data max will be set to the highest value that has been seen. Alright, so calculate average. This is fun. I like reading through code that I've never seen before and just trying to figure out what it does. So calculate average. Data average equals sum plus 10 divided by 20, calculated by 10 times to improve accuracy. Okay. Calculated by 10 times. That's odd. But, okay. Now there are some magic numbers in here which probably should be derived from other things. So, okay, we're down around line 367. Let's see, rec length is probably defined up near the top. Where is rec length? 200, size of wave data buffer. Okay, so I've been saying it was probably about 10, but I was way off. Okay, so it takes 200 samples. Rec length, where were we? Here we go. There, that's where we were. Data average is sum plus 10 divided by 20. Okay, data average came from, sum came from back here. So sum equals sum plus d. So this is accumulating all of the values. So if rec length is 200, it's taking the 200 samples and just adding them all together. So by the end of it, sum, data average, sum divided by 20. Why is that dividing by 20? That should be dividing by rec length, shouldn't it? Adding 10. Very odd. Okay, my brain can't quite compute what's going on there. Like, why is it adding the 10 and then dividing by 20 instead of 200? Or rec length. Or rec length divided by 10. Maybe divide by rec length divided by 10, just to make it more self-evident. Okay, so desired displays max min value, range min, auto range, no, yeah, okay. I'm not going to go into this in great detail. Range round up 10, range max. If more than 1020, hold, so that's applying a cap. So yeah, that's a constraint. There is a specific function for constraint as well, which isn't being used here, but this is a perfectly valid way to do it. All right, I'm sitting spinning on this code now in my brain. So if vrange is less than 1, so if auto range number is less than 1, so auto ranging is on. So if auto ranging is on, range min is data min minus 20, maintain bottom margin 20, range min round 10, okay. So it's dividing by 10 and then times by 10, which means what that's doing is rounding off the number, because if range min is an integer, then where is range min defined? Range min, it's probably somewhere back up the top. The effect of taking an integer, dividing it by 10, and then multiplying it by 10, which seems like a redundant operation, what that actually does is drop off the last digit. Well, it rounds the last digit. Because when you divide an integer by 10, you lose the last digit because it falls to the right of the decimal point, and then you multiply it by 10 and it moves back across again. Use Control F. No, I'm not going to bother looking for that. Range max, so if range min is less than 0, range min is 0. Once again, it's a constraint. Doing the same thing here. Attenuation, if attenuator is used, display range is determined by data. Upper limit is up to the full scale. Range max, LSB, so LSB, my guess is least significant bit, 50V. Write necessary code here, none for now, if fixed range. Okay, trigger position search. We're getting more and more into the curly parts of the code here, and I do want to stick the display on and actually make this thing work. It's interesting looking at all of this, but we could spend a lot of time investigating how this code works and not actually get to using the thing. Find the points that straddle the median at the center plus and minus 50 of the data range. There is some clever stuff going on here. Okay, so trigger point. Recording length, so that's 200 divided by 2, so that'll be 100 minus 51. Trig P, so it's a loop. Okay, so for, it's a for loop, and is that trigger point plus plus. Yeah, this is clever. It is looping through samples that are in the mid part, yeah, of the data range. Trigger point minus 51 and plus 50 to give it the boundaries around it. Nice. Positive trigger position found. Trigger direction is negative, negative, yeah. Okay. Clever. Let's move on. Freak duty float. Void freak duty cycle. Okay, so it's duty cycle calculations. Swing center. Calculate wave center value. Yeah. We could dive into this in great detail and I could spend the rest of the stream figuring it out. Let's not do that. Negative slope search. Duration search. Yep. I'm just going to take it on face value and not even going to read that. Wave frequency, some start screen. Okay, and then it's just got some display stuff. So this is just putting values on the screen. Display hold, display info, horizontal sweep speed. Okay. Draw fast line, trigger polarity. What I'm just wanting to get to. So most of this display stuff is going to be simple. It's just displaying text. Total poor man's oscilloscope, radio pinch one. Then most of it's just text. I'm looking for where it's doing the lines. So sweep speed, these are just fixed lines on the display. Trigger polarity, OLED print. It's using hex values for that. Up mark, down mark. Draw fast line, these are all hard-coded values again. I'm looking for the bit where it is going to do the actual waveform. So data, abs, blah, blah. Set cursor, print, yep, don't care about that. Vertical scale lines, yep, that's cool. It's just looping through and drawing some lines. Frequency display, yep, that's all cool. Plot data, here we go. Okay, so y1, y2, int x0, x is less than 98, x plus plus. So we've got a loop up to from 0 to 98. Then y is mapping wave buffer, trigger point, range min, range max, onto that. So this mapping function takes two ranges. It takes this range, no, what am I doing? It's taking this as its input, and then it is mapping from this range onto this range. So range, whatever the actual range min is going to be, gets mapped to 63. Whatever the range max is, gets mapped to 9. And then values in between get mapped proportionally. Now, interestingly, range min and range max, that should be a lower value than range max. And here it is a higher value and a lower value. So this 63 and 9, which look like magic numbers, they will actually be physical coordinates on the screen, and it'll be an offset. Now the way these OLEDs work, I'm pretty sure the origin is top left, which means positive numbers go right and positive numbers go down. So what this will be doing is, in the y-axis, which is vertical, a value of 63 is physically lower on the screen than a pixel position of 9. And that's why it looks like this mapping is backwards. So we've got a minimum value and to a maximum value mapped to a 63 to a 9. So it's just vertically inverting the scale. And then it's doing a constrain. Okay, cool. So it's making sure that it can't go outside of that range of 9 to 63. And Y2, so mapping there. Oh, Paul says, I like how every line of code has an explanation comment. Yeah, yeah. This is cool. I like this. Very educational. So we've got Y1 map, Y2 map, and then OLED draw line. So it's drawing a line. What we're doing is we're stepping through X, and we're drawing 99 samples, it looks like, because we're going from a value of 0 to 98. So it's less than or equal to 98. So it's going to draw a 0th sample up to a 98th sample. So we've got 99 samples, and that's going to be stepping across 99 pixels. So that is physical pixels on the screen that we're mapping here. And so the X position, so what we're doing is drawing a line starting from the offset. So 27 must be number of pixels that it's offset from the left side of the screen. So the first value that we draw, position 0, is going to be at pixel 27. So it's going to be X value 27 pixels in from the left, and the Y is going to be based on this calculation here. And then the end of the line is based on the X and then the Y, which is this calculation here, and then it just draws a line between those 2 points. So it's a start point, that's the start point of the line, that's the end point of the line, it's a white line, and draw it. Okay, so save stuff into EEPROM, cool, load EEPROM. I'm not going to go into that. I've got to get the soldering iron going. Aux functions. We're almost at the bottom. Pin to IRQ. Oh, there's a an interrupt request thing there. So there's an IRQ handler, which is being used for detecting when the button's been pressed. Ah, okay. So this explains why it's got the weird diode set up. Because what it's doing is using a pin to interrupt in order to detect when a button has been pressed, and then when the button is pressed. So it's not scanning the buttons, it's just waiting for the interrupt to be fired, and then it's checking which button has been pressed. So you can press any button and it will fire this interrupt. And if we switch back to here and the schematic, this suddenly makes a whole lot of sense. Because see here, we've got D2 coming in here, and we have these buttons connected via these diodes and this 100 ohm resistor through to D2, and there is a capacitor on there for a debounce, I guess, 100 nanofarad capacitor. So what happens is, if you press any of these buttons, what will happen is it will, the interrupt on D2 will fire, and then, because you can see that these buttons are connected to ground, so they link to ground. When you press switch 1, for example, what it's doing is connecting it connects to ground on this trace here, which comes to D8, and through this diode. So the diode is reverse biased normally. Well, it doesn't really matter in this case. What's going to happen is that it's forming an open collector thing. So when you press this, it will pull to ground on here, and my guess is that there's an input pull-up turned on in the code on D2. So what will happen is that this will be high normally when you press a button. If you press any button, it pulls this input low, which then asserts the interrupt, and then, because the interrupt has been asserted, it calls this function here, and then once it's got there, it will read each of these inputs, so D8, 9, 10 and 11, and it will then be able to detect which button has been pressed. So you can press any button, it fires this IRQ, and then you say, was it this button? Yes or no. Was it this button? Yes or no. And then do appropriate things depending on which button has been pressed and which range you're in. Cool. So the nice thing about this, with this approach, is that you don't need any code in your loop which is polling those buttons, because the obvious way to do this is to do a digital read on each of those buttons in your loop, and then if it's been pressed, you do something about it. But the problem is that takes time. And as we've already seen, this is really, really pushing as fast as it can to take all of those samples and then deal with them. It really can't afford to be doing anything like just checking if a button has been pressed every single time it runs through the loop. So if we look at where this has come from, we can see back up here this will be in setup. Setup, yep. So this is in setup. What it's done is attached an interrupt, and the interrupt handler has been defined as pin 2 IRQ, which we've just seen. It's interrupt 0, and which is on digital pin 2, and it's falling. So when it goes from a high value to a low value, the interrupt will fire and it will invoke this particular function, this interrupt handler. Yes. Scott says, should make the buttons work despite heavy use of blocking code. Yes, that's right. It should always respond. Chip says, it seems well thought out. Yeah, it does. Yeah, this is really quite educational. I like this. There are some interesting little tricks shown in here. And yeah, when I first saw this, I was a bit baffled by this diode arrangement. I didn't immediately see why this was being done, but it was done for a very specific reason. So the hardware design here has been partly dictated by the software, the needs of the software, which is cool. All right, let's stick some pin headers on this thing and load some code and see what happens, because I want to see it working. All right, I need to find, what do I need to find? I need to find myself an OLED. All right, I have somewhere around here, I have a box of, oh, ow, moving hurts. It's the after effects of Muay Thai yesterday. And no, that was not what I had for dinner. It's so 128 by 64, yes. I think these are what I want. Got a whole bag of OLEDs in there. Oh, DIY is here. Cool. Oh, Dodgy asks, so is it only monitoring D2 every time? No, it's not monitoring D2 at all. This is the trick with the interrupt. So what happens, I do want to, oops, which one? That one. I do want to get on to putting this hardware together and running it. But the trick with an interrupt is that once you have set it, it is handled in hardware. You don't have to care anything else about it. So we've got, where are we? Okay. So we've got this attach interrupt in setup, and this is, it's setting a hardware function within the microcontroller. And what it will do is that if these conditions are met, so it sees a falling edge on this input, interrupt 0 being D2, then it will invoke this function. But that is done largely in hardware, so you don't ever need to do this again. You don't need to check D2, you don't do anything. All you've done is defined an entry point in your code, or a callback in your code, that will be executed when this condition occurs. So we've got, if you look in loop, if we look through here, there will be absolutely nothing. I haven't read this now, this time, other than just earlier. There will be nothing in this to do with reading D2. It'll never be referenced anywhere. So we've got set conditions, read wave, digital write, set conditions, start analyze, write common, plot, display info, save EEPROM, blah. There is nothing in here that needs to be called to check whether any of the buttons have been pressed. It becomes a zero overhead function, which is really, really nice. And this is very useful for things like reading high-speed inputs, like optical encoders coming off wheel, like an encoder wheel on the back of a motor, that might be spinning and giving you 5,000 or 10,000 pulses a second or more, and you need to be able to count them. You can't just keep polling the input to check whether it's been set. You set it in hardware and it executes extremely quickly. Dodgy says, okay, get it now. Never played with interrupts before, so it never calls any code unless the interrupt is triggered. Exactly. You've got it, Dodgy. So it's a very, very useful and powerful little tool. So back to the start of the code here. So this is saying screen width 128, screen height 64. And that, I think, qualifies. I'm pretty sure these are a SSD 1306, SH1106. Maybe it's not the correct type. Let's see. There is a, what other displays do I have in here? 128 by 64. Oh, 64. No, what was that? 128 by 64.96. Oh, I think this might be it. Okay. That is a 128 by 64.96 inch white. It's 128 by 64, 1.3 inch blue. These ones have got the SH1106 driver chip on them, I think, and I think these are the SSD 1306. So I'm pretty sure this is the type that I need. Now, to be safe, do I put a header on the shield and then plug this into the header? Oh, Johnny, generous, thank you very much. Johnny has just gifted a whole bunch of memberships. So what I could do is solder a header on here and then plug the display in, or I can solder it straight to the PCB. I think I might put a header in and I'm going to play it safe. Yes. Yeah, Henrik says header. I think that is the appropriate thing to do in this case. Cable tie, never fear, cable tie is here. Yes, thank you for coming along, cable tie. Have you been out on the bike today? Looks like a pretty sunshiny day. A little bit chilly out there. The descent coming down Mount Dandenong would be cold, but yeah, not a bad day compared to some we've had recently. It would be an alright day to be out on the bike. Let's see, I'm just going to mess around with some headers and things on here. What have I got? So that will be for the display. And I also need, let's see, which Arduino should I use? This one, I'll try this one. And I will also put some pin headers into this. If I can pick them up. What do I need? Unfortunately, I think I have to put all of the headers in it because it uses a few out of different parts of the thing. What's that, an 8-way? Yep, that's an 8. That's another 8, we don't need that. I need a 10. So I'll stick that in there and break it off. And I need a 6. I can't immediately see a 6. So let's just stick an 8 in it, break it off. Oh, broke off too much. Oh well, let's do it again. Put that in there, snap it off. There we go. So, got the headers in the Arduino. Stick the shield on top. Oh, it doesn't quite clear there. Interesting. The power, I'm going to have to trim this a little. Somewhere I have put down my nice Lindstrom cutters and I don't know where they are. In fact, I'll cut those off as well. Just the mounting stakes for the connector. So these cutters are, yeah, they're quite dodgy. They've got hacked blades on them. Ah, come on. Is my coordination that bad? Yes, it probably is. Okay, so now it's sitting down on the power connector a bit better. Time to get out the soldering iron. So, alright, I'm sure you've been chatting among yourselves a bit as well, but what projects have people been working on recently? The usual filler question. What have you all been up to? Dodgy, have you been working on your lawnmower again? That was having some good progress I saw just a little while ago. I do feel like I need a drink now. Oh, my stomach is gurgling too. I think that's because I haven't had breakfast yet. I was, because of previously mentioned poorly managed late night and sleep and stuff last night, okay, now that's on. Unplug it. Where was I going? Oh yes, lack of sleep management. I was slow getting up this morning, and I had to take my daughter to the railway station as well. So I ended up getting here only a few minutes before the stream was due to start, and did not end up eating breakfast. So I need to do something about that. So the lunchtime call is going to be the breakfast call. Oh, my stomach is still going. It's just going blah, blah, blah. Alright, display. I guess it goes down. Because otherwise it would cover the buttons. Alright, stick this back into the Arduino. And let's get some code on this and see what happens. Alright, what do I need? And I need a micro B connector. No, micro A. Whichever. One day I really should figure out which one is which. What is that? That's USB-C. That cable is no good. Alright, I need a... I need a USB cable. And I should have thousands of them here. I know that I actually do literally have thousands of them here. They're in a box out in the factory area. I'm just trying to avoid going out there. What have I got? This one. Okay. This cable should do. I'll plug that in. And the other end, plug in here. Oh, too much stuff piled up on my bench. All right. Plugged in. And no smoke came out. So let's see what happens. What have I got? I tried compiling this earlier. So I got Uno, port, it'll be that one. And yeah, let's just go for it. Compile and upload. Ooh, Jordan, congratulations. Jordan said, latest project, getting a new job, status complete. Yes. Dodgy said, are those BNC connectors? I believe they are. Where are we? Henrik says, you heard the stomach. DIY in the Ghetto says, I'm working on an I2C to I2C project, talking between two Arduinos. That's interesting. That is, yeah, that is not a common thing to do. So, where are we? Eventually you have infinite singles. What are they doing? Always buy pin headers in 40 pin lengths. Yeah, I do. Single pin headers. Oh, okay. What am I doing? I don't know. What am I doing? Did this upload? Yes, it said it uploaded. Did I've got no display. I don't know if that's a bad sign. All right. Oh, Keith said, I'm setting up Octoprint after seeing John set up last week. Oh, cool. So the barbecue was useful for inspiration. Ah, Jordan says, next project, moving to a new state. Ah, so does this mean that the job that you just got is in a new state? That is that's a big thing. Ah, Scott says there are no micro A connectors. No, okay. There's only mini B. There's micro and mini. Icky says, I'm trying to get the radio library to work on the Seed E5 LoRa blob. Ah, tricky, but if anyone can do it, you can. I have faith in you, Iggy. So Henrik said, is the SCL SDA pins match? Ah, okay. That is a good question because these displays do come in different things, different versions. Ah, cool, Jordan. So moving for work. Right. Yeah, Scott says micro and mini are both B connectors. Yes. I need to print out a diagram and stick it over my computer or something. All the sizes are on B. A is on the PC side. Huh. Cool. Yeah. Oh, Wagon Load says, I've seen OLEDs with power reversed. Yeah, so it could be. I need to get back to this display, this version. This camera view. Those are the words that I'm looking for. So at the moment this is powered up, and you can see that there's power under there. And buttons. But I've got nothing on the display. Which could be, and the display is significantly warm. That is, yeah, that's not a good sign. Okay, let's check. DIY in the ghetto says, make sure the power and ground as well as SDA and SCL pins match. I had that problem to where I killed an OLED. Yeah, it may not be the same. All right, let's have a quick look at the pinout that is on here and compare it to this display, because these displays do come in different versions and they can look identical and have the pinout in a different order, which is probably what's going on here. So I probably just need to use some jumper wires or something to connect the display instead of plugging it straight in. Michael says, here comes the smoke. Yeah, if I leave it plugged in, maybe we could really get some smoke. All right. And Henrik has just sent me to the editor for the board, which is very kind of you. Thank you. All right. So what do we have? This is the board. How do I zoom in easy EDA? Okay, so there's the OLED connector, and according to the notations on here, it's 5 volts, then ground, and then A5 and A4. That'll be SCL and SDA, or vice versa, whichever way. Now, checking my display, ground. Yeah, that looks right. Oh no, it's ground and VCC are reversed. You probably won't be able to see this. Hang on, I'm going to see if I can get this microscope to run without turning itself on and off repeatedly. Get some focus happening. Yeah, look at this. This is the header on my OLED. So it goes ground, VCC, SCL, SDA. And if you look at this, it goes 5 VCC ground. Yeah. I let the smoke out, except there was no smoke. Very unfortunate. Now, what I also don't know is whether A5 and A4 are the right way around. Johnny, thank you for the donation. Yeah, it got warm, but no smoke, no actual smoke. All right, so I just need some jumpers, and hopefully A5, which way around is it? SCL, SDA. So hopefully A5 is that way. A5 is SCL and A4 is SDA. I can't remember. Okay, So I need some jumper wires to remap. I seem to have a shortage of male to female jumpers at the moment. Where? Breadboards and jumpers. I've got this box of assorted jumper wires and breadboardy things, and I've got plenty of male to male jumpers. And where are the male to female? Why is there a servo in here? The random servo in the box. So, oh, there's one. There's one. It's a red one. I got some that may at one point have been cut like this. So, oh, hang on, what's that one? Oh no, that's end of the servo cables. Where? It would be annoying if I can fix that with a pin. I need to order some more jumper cables of the right type. I just do not have the right ones. No, that's male to male. Come on. How can I be stymied by such a simple problem? I'm kind of tempted to just solder some wires onto the OLED to avoid this whole problem. Alright, let's get some. So there's a black and I'm going to do it, a red, and then how about orange and white can be the other two. They will do. Okay, so I'm going to solder these onto the display. But what I'm going to do is grab a new display, because I suspect that that other one is no longer in the land of the living. Henrik says just use breadboard. Yeah, I could. That's true. Let's do that. That's even easier. Gotta get the display out. Gotta keep track of which one is which. Alright, this is the new display. It's a long time since I've used a breadboard. But I do have them right here, so let's do it. It's a dodgy, dirty looking one. I think this one's been used a bit. It's all yellowed. Okay, so now we stick the display in there, and then we're going to go VCC and ground. So they need to be swapped. I should unplug this, shouldn't I, while I'm doing this. And then SCL, SDA. So what I'm going to do is just swap the wires here. So I'm going to go VCC ground. They are the opposite of what they were before, and then I'm going to just map SCL and SDA directly, the same as they were before, and plug it in. Let's see if we get something. Oh, come on. Coming up on the display. Oh, we do! Look at this! Oh, it's a pity that it's flickering on camera, because that is really quite pretty. I like that. I'm going to take the plastic cover off it. On camera, like from what you can see, that is flickering like crazy. But for me, that's looking... Woo! Okay, silly question. Why are there two B and C connectors here? Let's have a look at what is connected through on here. Oop, zoom out, zoom out. Which one do I plug into? So that signal, oh, okay, it's just two connectors going to the same place. Is that correct? And why is that looping around there? Ground, okay, so that's ground. What is that one? And why is this net separate? I don't understand that. Okay. Dual trace Oscilloscope. No, but it's only a single trace on the schematic. And what we can see here is that the center pin, which is the signal pin, is connected together. So they both will go to the same place, as far as I can tell, unless I'm misinterpreting this, which is quite likely. So we've got the center pin from the top connector coming to this 520k resistor, and we have the center pin from the bottom connector coming to the 520k resistor. So it looks like we have both connectors going to the same place. Oh yeah, so Henrik says, I fixed it in my new PCB. Cool. Alright, so it doesn't matter which one we use then. They should do the same thing. And also you can see there are these 4 pins here. So these 2 pads on the front part of this connector and the 2 pads on the back part of this connector are connected together, and vice versa. But in fact, on the body, these are all just electrically, these are all ground, all 4 of these mounting points. So I see, so it's using that as a way to get ground to there, but then, yeah, okay, doesn't matter, it's fine. Yeah, as Wagon Load says, okay, connect a probe to the top one and a scope to the second one. Yeah, so you can use it like a daisy chain sort of thing. It could be signal in, signal out or something. Oops, you can't see that. Yeah, so we could do signal in and signal out or whatever. All right, let's make stuff happen. I'm going to turn on. Oh, also, what I didn't check was in the code. Does it send anything to the serial port? I don't think it does. I think it only displays. So setup serial.begin many RAM many RAM used when activate this maybe crash. Yeah, okay, so there's no serial output from this, which means that I can't bring anything up on the screen here to show you. The only thing we can see is the actual physical display, which is right there. I'll zoom in on that later, but what I'm going to do first, while we still got this wider field of view, is connect the, just grabbing myself a power supply lead for the function gen. So the function gen needs 5 volts, VSET 5, go, and a surprisingly large amount of current. Did everybody hear my stomach then? Okay, function gen power on, Unity. All right, now just before the stream I grabbed some random leads. These are leads that came with the function gen. They've just got alligator clip outputs, but there is also this other lead which I think will do what we want. What have we got? Channel 1 out. All right. Oh, sorry, I'm just moving this to where I can get to it easily. All right, channel 1. How can I arrange this so that you've got the best view? Moving things around a bit. I'll move that over there. I'll move that down there. And what am I doing here? I don't know. All right. Doesn't matter which one I plug it into, so I'm just gonna plug it in there. Turn on channel 1. Turn on channel 1. What have we got? All right. Let's see what these buttons do. That looks like it's the hold button. Oh, that's changing the time base. Or is it an auto ranging? 50 milliseconds, 20, 20. Oh, I see. So that's select, and this is up and down. All right. Okay, I think I've got the menus now. Average 10, 50, right. All right, now what am I doing on here? Let's set ourselves up. Frequency, Channel 1, let's go for well, it's a 1 megahertz signal. I was just going to try something really low. Let's see, megahertz. 100 kilohertz. That'll do. Amplitude 3 volts peak to peak. I suppose that'll do. Offset 2.4 volts. Let's make the offset yeah, I don't know, whatever. Phase 0, duty cycle 50%. Phase 0, duty cycle 50%. I don't know what I'm doing. Okay, so we should have a channel 1 square wave doing 3 volts peak to peak at 100 kilohertz, I think. I should connect my actual oscilloscope and see what's coming out of this. Oh, yeah, probably an Arduino based scope. Dr. Z's? Oh, Dr. Z's is here. Thanks for coming along, Dr. Z's. Yes, so it is a kit oscilloscope, which was created by, so this PCB was created by Henrik. And, Henrik says, I don't think I messed up the schematic, but I don't know. Okay, well, we can figure this out. Where was I? That's right, I was going to grab my, my actual oscilloscope so I can see what is coming out of this function gen. And just to be on the super dodgy side, I'm going to use this alligator clip thing and plug it into the pass-through so that I can then connect this to the actual oscilloscope. I shouldn't say that because this is an actual oscilloscope. It's like I was being derisive, but no, it's a it is a good thing. All right. What have we got? Channel 2, unfortunately you can't see this. I'm going to turn off channel 2, and what I am seeing is indeed it's saying 3.4 volts peak to peak, and it is, what have we got? Vmin minus 1.7, Vmax 1.7. Oh, okay, I need to fix the offset. It'll be driving to a negative value on this, which is kind of sucky. All right, offset. So offset, come on. No, that way, that's better. Offset, take it down to about there, 1.6, that'll do it. So low 174 millivolts, high 3.174 volts, that should be fine. Okay, now I'm just having a look on my other scope. All right, so now we've got minimum of minus 80 millivolts, which is still a bit below. That's odd, it should be saying positive 174 millivolts. So I'm gonna take that up. Okay, that's better. All right, so now on the Rigol it's showing about a 0 volt minimum, about a 3.3 volt peak, and that is about, you know, approximately what we expect to see. What I'm not seeing on here is a signal that matches anything like that. So what we've got is the signal gen bringing the signal into this connector, doing the stuff on here, passing through to this connector, which is coming out to here and going to the Rigol. And the Rigol connected to here is seeing a square wave at, what is it seeing? 100 kilohertz, 50% duty cycle, 3.3 volt, square wave. It is seeing what this is generating with a bit of noise. The signal does not look that great, but that's, you know, I've got stuff hanging off here. So, next question is, what is going on with this and what is it saying? So it's saying AV 10 volts. It's possible that I killed the analog input on the Arduino by feeding it a negative voltage out of the function gen, but I don't know. Hold. Okay, so what time base should we be looking at? Probably, let's see, okay. Oh, Henrik is calling me. I can't answer, Henrik. I'm on a live stream. The fix is in your DC. Okay. The fix is in your DC. There is a problem. The resistor point where we discussed earlier. There isn't a trace going into A0, so you need a bodge. Cool. Okay. Okay, so we need a bodge wire to get into A0 from here, which is why we're not seeing any signal on here. Rightio, let's do that. Now, I'm going to switch back to this view and back to here so that we can see where this needs to be done. Okay, so what we've got is A0 is down here and there is no trace going to it. So it's not going to be reading anything. It's just going to be picking up random noise. 90-second bodge. No, you're not, Henrik. Do not say you're dumb. This is pretty impressive. So what we need is a connection to A0, and if we go back to the schematic we were dealing with here, A0 needs to come to this junction point coming on the inner side of the 510k resistor. So the 510k resistor is this one here, except this one says 520. So 520, 510, doesn't matter. 510, close enough. So 520 here. So this junction point here, right there, this is where the signal will be. And we need to bridge that down to A0 down here. Easy. Let's do that. I like fixing things with solder. So, all right, I'm going to turn off the signal, disconnect that, disconnect USB, because I don't want anything live while I'm soldering to it. And what we can see is, where's my little thingy of jumper wires? I need a short bit of wire to go, now where are my dodgy cutters again? To go from A0 to that point there. So just a little bit of random IDC cable. Let's see if I can strip it with these dodgy cutters. Yeah, I can. All right, I'll cut it a little bit shorter. Yay for signal integrity. Where's the solder? Over here. I'm trying to do everything in a little area so that it's on camera. All right. Get over there and tin that wire. Come on. Tin that wire. All right. Solder it onto A0. And I'll do this with tweezers so my annoying hands aren't in the way. And solder that onto the junction point right there on the inside of the 510/520k resistor. There we go. All right. So now get the solder out of the way before it falls on something and causes a short circuit and becomes the fuse. So now I'll plug my that's the input side coming from the function gen. This is the output side going to the Oscilloscope. Plug in USB. Oh. Come on. Is that plugged in? Can't even tell. Okay, yes it is. Okay, so it's booted. Now I'm going to start the function gen again. And, ooh, we got a change on here. It is, yeah, average 3. This is actually doing something. Let's see what we can do. So what I've just done is, well, if I hold it, I press the hold button, we can see that it's saying average 3.25 volts. So the time base is totally wrong. It's on a 20 millisecond time base. It's way too slow at the moment. What we could do is run a really slow signal coming out of here. Might be better. So I'll unhold it. But we've got 20 milliseconds. Okay, I'm going to do two things. The select button steps across. I'm going to change that to a 10 volt, no, to a 5 volt scale. Okay. Then I'm going to step across to the time base. Which way do these menus go? 10 milliseconds, 5 milliseconds, 21, 500 microseconds, 200 microseconds, and it's saying unsynced. So what we can see here is jumping around. That is actually finding an edge of a signal here, and it's a little bit hard to see because of the scan rate on the camera, but that is actually showing an edge of a signal. So let's slow this down. Let's go for, let's just go for, say, 10 kilohertz. Ooh, look at this. We can see a waveform. So now if I change the time base back to, where is it? Oh, that's on a 2 millisecond, 1 microsecond. Yeah, it's not showing us all that much that's useful, but it does seem to be kind of working. We're getting something coming out of it. So we're on a 500 microsecond. What am I on the Rigol? I'll set the time base on that to, if I set it to say 50 microseconds, oh, it's on 500 microseconds at the moment. How far can we go? 200 microseconds. We can't go below 200 microseconds. All right, I'm going to slow this down even more. Let's go to 1 kilohertz. There we go. Look at this. Look at this. We're seeing it. Success, Henrik. So we're seeing 50% duty cycle. It's saying it's 1 kilohertz, just jumping around a little bit. Average 1.75 volts, which is correct because we're running on a 3-ish volts, whatever the setting is. 3 volts peak to peak on this. And we've got a waveform. Let's try changing the time base again. There we go. Hang on, I'm gonna zoom this camera in. It's gonna go crazy for a little bit while I do the zoom, but I'm gonna get that centered on the screen because now I'm going to zoom this way in, and it's in focus assist mode at the moment. That'll jump back out of focus assist in a second, and it'd be good if it stayed in it. But there you can see the actual waveform on the screen. That is, yeah, did someone say zoomies? Yes. Signal matches the shape of the bodge wire, says Keith. Yes. Paul, thank you. Thank you for that super chat. No, not really super chat, it was a donation. Very generous. Yes. Henrik says, try to change the arrow in the screen. Yes, okay, so the arrow is the trigger direction, I think. So that, I wonder if I can get this under the microscope. That actually is probably a better way to be looking at this. All right, I'm going to try to slide all of this across without causing disconnects or, oh, hang on. My USB cable became the limiting factor all of a sudden. I get it there. I'm just going to do a bit of setup on the microscope. Oh yes, I think this is going to work. But first I'm going to have to, there we go. I'll switch inputs. Okay, so, oops, I'm right at the limit of the wire, the wire reaching here. So this is what the display is showing, and we are feeding it, according to the SIGGEN, a 1 kilohertz signal, 3 volts peak to peak, and you can see that the average there it's reading is 1.7-ish something, which is about right, starting from 0. So, Henrik, you have a successful little micro oscilloscope here. Stephen W says no flicker cam. Yeah, it seems to be behaving itself just temporarily. I kind of just jiggled it around a bit. There is something weird going on with it. All right, now the what I was just talking about and what Henrik was referring to earlier was the trigger. Now I need something small to point with. What can I use? All right, a broken off knife blade, knife tip, that'll do. So you can see on the screen just here, there is a down arrow. And what you can see is that there is the, this center point here is on a falling edge. So that means the trigger is on a falling edge trigger. Now I'm going to use the select button. See, each time I press the select button, it moves between those three things. It can be either the 5 volt, which is the voltage range, it can be 1 millisecond, which is the time base, or it can be that. Oh, look at that. That's because I had my hand near it. See, look at the signal now. This is with my hand nowhere near it. When I'm touching the buttons, look what it does to the signal. And this is the trigger. So so I've changed it to a rising edge trigger. And you can see, oh, there's the flicker. And you can see that it is now setting, see this, this graticule here, this vertical line here, is being triggered at that point. Very nice. Now if I press, so you can see that doing that is a rising edge trigger. It's on this up tick part of it, and if I change it to a falling edge trigger, then it's triggering on this falling part of it. Now I wonder if it's possible to change the actual trigger level. My assumption here, just based on what I can see, is it looks like it's triggering at the mid-range point. So this is on a 5 volt range. I guess this 2.5 volt line is the trigger level, but I don't know if it's possible to change the trigger level. So I'm just going to, just for the fun of it, I'm going to mess around on the SIGGEN and move, what am I going to move? Just bringing the bottom of the range up a little bit. You can see that I'm changing the low part of the waveform there, and the little micro oscilloscope is changing to suit. So I'll take the upper voltage up a little bit. Yeah. Duty, okay. How about I change the duty cycle? Look at that. So that is on a 20% duty cycle. In fact, I'm going to change the trigger. So trigger to rising edge, and that's 20% duty cycle. And then I'm going to, so the SIGGEN is currently set on 30%, and you can see that the analysis here on the oscilloscope is jumping around a bit, but it's around the 30% mark, give or take a few percent. Take it to 20%, increase the duty cycle, take it up to, it claims 80% now, and my my Rigol is now out of range. I've got to change the time base. It is now, yeah, the Rigol is measuring spot on 80.00%, and what we're seeing here is jumping around a little bit, but it is around 80%. This is really kind of surprisingly useful in terms of the number of functions that it does. It's a pity that the bandwidth limit is so low, because what we're looking at here is a 1 kilohertz signal, and it's kind of pushing the limits. Well, we're on the 1 millisecond range, so let's change the time base to, that's 500 microseconds, 200 microseconds. All right, I'm going to change the frequency up to, what will I do? I'm going to change the frequency to 10 kilohertz and see if we get a signal. Yeah, not really. Probably around 5 kilohertz, frequency 5. Come on. No, I don't want period, I want, how do I do anything in, oh, there we go, frequency 5 kilohertz. I think I was in the wrong thing. Frequency 2 kilohertz? No. Maybe it's the trigger. No. Why is it not seeing this? Hang on, my duty cycle is very high, so I'm going to decrease that. I'm going to make it 50% just so that it's easy to see if we do start getting something on here. Where am I? Back to frequency. All right. 2 kilohertz. Am I doing something wrong here? That's 1 kilohertz. Yeah, so that's on a 500 microsecond cycle. I have a feeling that we're running into timing issues with the Arduino. So this is 500 microsecond time base, and I'm feeding it a 1 kilohertz signal at 50% duty cycle. So if I go, instead of 1 kilohertz, if I go to say 2 kilohertz, so I'm going to go to 2 kilohertz. All right, now we can see the number of peaks on the screen, and we're in a 500 microsecond time base. If we go to a time base of 200 microseconds, you see how it's failing at this point. It's right on the edge of what it can process. What we should be seeing, so if we're going from 500 microseconds and we're seeing this many, however many, 1, 2, 3, 4 peaks on the screen, and then we switch to a 200 microsecond time base, we should just be seeing more peaks on the screen, but we're not. We're just seeing noise and stuff. It's failing at that point. So that is somewhere around the point at which it fails to be useful. So this is 2 kilohertz. Let's go up to 3 kilohertz. Let's go to 5 kilohertz. All right, so at 5 kilohertz, we can see that it is, well, it's giving us useful numbers. We can see it's analyzing it as being 5 kilohertz and it's around 50% duty cycle. So its analysis of it is actually quite useful. It's just not able to display anything much if we go beyond that. So if we go into the 200 microsecond range, it freaks out. Yeah, that should just be showing us, switching to the 200 microsecond range here, should just show us more detail, and it doesn't. So we've hit the limit of what the device can do. But, so practically somewhere around 5 kilohertz is the most that you can feed into it and see useful stuff coming out. But that is really, really cool. Oh, well, Henrik, thank you for sending me this. This is this has been a fun little thing to play with, and really interesting in terms of looking at the software and how that is processing the signal as well. There are some interesting little tricks. So Amanda says lunchtime now. Yeah. Where were we? Where was I? Back to here. Yeah. I hope people found that useful. I find it really interesting and useful to look at this sort of thing. So the IRQ handler is a useful thing to know. So the way it did those buttons with the interrupt coming off D2 to be able to avoid scanning any buttons and yet respond immediately if any button is pressed. Henrik suggested trying sinus, which I guess is sinusoidal, rather than square wave. So yeah, okay, I can try that in just a second. Oh, it's already 12. It's already 12:15. All right, let's try this. I'm going to try. Can we see anything there? No. Can I move this? I'm going to try to get it so that I can switch between the two views. Without moving that, I want to move this and get it into the camera view, kind of. That is dodgy. All right. What am I looking for here? Wave. Wave, I'm going to go for a sine wave, leave it at 5 kilohertz. And everything else the same. Okay, so I've just changed to a 5 kilohertz sine wave. We're doing about 4-ish volts, give or take. And that's it. So if we now switch back to the view that's on the scope, you can see it does actually kind of look like a sine wave. All right, so I'm going to go to the 200 microsecond time base, and it still doesn't handle it. So let's try going for, let's put it back to 1 kilohertz, just because that did look quite cool. And then back to here. All right, so we've got a 1 kilohertz sine wave coming in, 50% duty cycle. And does a duty cycle even make sense? I keep saying duty cycle and we're talking about a sine wave. Does it even make sense in this context? It probably does. Yeah, so 200 microsecond, still doesn't see it. All right. So it looks like the 200 microsecond time base is not useful, but that does look cool. It looks cool at 500 microseconds. Yes. Scott says, still want to see what happens if it drops below 2.5 volts. And Wagon Load says, try to modify the code to use a pot on A1 as an analog trigger level adjustment. Well, since we are here and here, where is that trigger? I don't remember where the trigger stuff was, or what. I have a vague recollection that when we were looking through the code, we saw that it was triggering at half of the, is it trig? Oh, here we go, trig sync. It was looking, find the points that straddle the median at the center 50% of the data range. Oh, right. Yes, we did look at this part of the code. So it is a dynamic trigger level. That's clever too. That's very clever. So it's a dynamic trigger, not a static trigger, and it is based on the range of the readings that you're getting. So it looks at what is the minimum, what is the maximum, finds the values at the midpoint, and then uses that at the trigger. Yeah. So we could put a variable trigger in. You could have a configurable trigger, but this way of doing it is nice because in most situations it will simply do the right thing. It'll trigger at the midpoint of the line, at the midpoint of the samples. So yeah, I don't have a problem with that. That seems reasonable. Yeah, clever stuff. Right, okay. And now, since I failed to breakfast, I am going to go and have a combined breakfast, lunch. Maybe I'll just have breakfast cereal for lunch. Dr. Z's, yes, well, great to see you along too. I haven't seen you in chat or anything for a long time. So, yes, brunch, second breakfast. Yeah, so there's breakfast, second breakfasts, 11s. Yeah, I don't think he knows about second breakfast. Gerald says pizza with bacon. Cereal for lunch is the best, says Chip. Right. Well, firstly, thank you again to Henrik for sending me all of the cool stuff in that package, all the things to play with, and your funky little oscilloscope project kit thingy. That's groovy, and it's been interesting seeing it and how it works, looking at the code, and that the range attenuation thing in the with the digital output that's driving a variable voltage divider. That's pretty cool. There are some interesting tricks in that project. Scott says pancakes, bacon and real maple syrup. Yes, that is the classic Canadian breakfast. I am very tempted. And you know, the funny thing is that is something that I can eat and enjoy without screwing up my stomach, because I have gluten-free flour, which means that I can make myself gluten-free pikelets. I have bulk bacon, and bacon is fine, generally fine with Crohn's. And if you buy maple flavored syrup, it's normally sweetened. It's basically like fructose. Yeah, it's really bad. I can't have it. But genuine maple syrup has a reasonably low fructose level in it. So I can do bacon and eggs with maple syrup on pikelets. Yum. All right. Log off, John, says Peter. He is telling me to get lost. All right, I will get lost. So, thank you everyone for coming along today, and it's been a fun time. I like it when I get to fire up the soldering iron. All the good things today. We got to play around in code, we got to solder stuff, and we got to see things running on a board. Yes. Yes, electronics over. Next in this channel, Cooking with John. Thank you everybody. I am going to hit the big red button now, end the stream, and I will talk to you all. Hopefully I will talk to you next week. There is a slim possibility I won't. My good friend David, who I train with in Jiu-Jitsu, is competing next week and on Sunday, and I really want to go and see him compete, but I don't know what time his event is going to be on. I hope it's in the afternoon, so I can do the live stream in the morning and go to the Jiu-Jitsu competition in the afternoon, but I shall see. So, hopefully I'll see you next week, and goodbye, farewell, and amen. See ya!